All right, so this is a short introduction into organic chemistry. We're going to look at some naming rules and we're going to look at some basic concepts behind organic chemistry. So let me grab a pen and we'll get to this. Let's go with white. All right, so a lot of stuff on this slide. Let's just kind of look at it real quick and then move on. I know you guys can read, right? So basically, organic chemistry looks at things like petrochemicals and pharmaceuticals. Those are two of the most important parts of organic chemistry that probably affect your daily lives. So petrochemicals are things like gas and diesel fuel. Vaseline is a petrochemical, stuff like that. Pharmaceuticals are our aspirins, right? Our medicines, vitamins, insulins, that kind of thing. And another science that is, important to organic is polymer science, which we'll look at a little later in the slides about plastics. Now, when we talk about what we're studying, what we're looking at is the structure and function relationship between the molecule itself and the properties that that molecule demonstrates. Okay. Um, Carbon is pretty unique as far as the elements are concerned because it can form really, really, really long chains. Okay, and the longer the chain, the more variety you can have in your substituents or your side groups, which makes all of the different complex molecules we need to be alive. It makes all of the different complex molecules in the petrochemicals and the pharmaceuticals and all of those things. Now, when we look at carbon chemistry, we're going to talk about hydrocarbons, which are carbon and hydrogen groups. We're going to look at functional groups, which are side chains on a parent carbon molecule. And then we're going to look at some complex polymers like plastics or, things like lipids or triglycerides, right? Our biological molecules, proteins, that kind of thing. So, first thing we need to understand is that there are three basic groups of hydrocarbons. There are the alkanes, the alkenes, and the alkynes. Alkanes are single bonded hydrocarbon chains. So it helps if we draw these out. So probably the simplest alkane, well, actually the second simplest, would be this molecule right here. All right, this is ethane. Ethane, and we'll get more into how to name this in a minute, but the ending ane tells you it's an alkane. All right, it is the carbons only have single bonds between them. We consider this saturated, which means it has all of the hydrogens it can possibly have bonded to each carbon. And the general formula for this is CnH2n plus 2. So let's see if that's true. Here we have C2 and we have H, and we have 3 on the left, 3 on the right, so 6. So 2N would be 4, plus 2 is 6. So there we go. Now the simplest hydrocarbon is methane, which is just CH4. And again, we can see that it has all single bonds. It is saturated. And again, you have CH4. So 2N plus 2. 2 times 1 is 2 plus 2 gives us 4. An alkene has at least one double bond. So ethene looks like this, right? And Vesper is what tells me, hey, make sure those hydrogens are as far apart from each other as possible. So I don't do them straight up and down. I do them at an angle. This would be ethene, E-N-E. And that ene tells me there's a double bond present. This is CnH2n. So we have C2H4, so they're just doubled. And this can be either unsaturated, which means some of the carbons don't have the maximum number of hydrogens, right? Like carbon should have 3, but these only have 2. Or it can be polyunsaturated, which means multiple carbons in the chain don't have all the hydrogens it needs. And finally, there are alkynes. The simplest alkyne is this one right here, a linear molecule. It is ethine, Y-N-E. And the ine, it tells me there's a triple bond. Again, it's unsaturated, in this case, polyunsaturated. And our general formula is CnH2n minus 2. So C here is 2. So H2n minus 2 would be 2 times 2 is 4, minus 2 is 2. So there's our formula. All right, there we go. So alkanes are single bonds, alkenes have double bonds, and alkynes have triple bonds. These can be more complicated than that. All right, so like here's an alkane that we would normally draw. Now, let me take a moment and kind of show you what this is compared to what we were just now looking at. So in organic chemistry, it is customary to leave out the carbons and to leave out the hydrogens. So this is 1, 2, 3, 4 carbons. So this is the same thing as carbon, 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 carbon with all these hydrogens. All right. These two things are equivalent to each other. This is the one that we draw, right? Because it takes up much less space, all right? We don't have to draw in all these little hydrogens and everything. When you're talking about organic chemistry, you are working with an understanding that all of the carbons have 4 bonds. And if nothing's written there, it's a hydrogen, all right? So let's look at this thing again. So there is our, we have 1, 2, 3, 4. So this would be butane. Again, ane at the end. All right. So let's talk about how we name this stuff with the IUPAC system. The International Union of Pure and Applied Chemistry is what IUPAC stands for. And the prefix system is really simple. You need to know 4 new words or 4 new prefixes. 1, 2, 3, and 4. Meth, eth, prop, and bute. After 4, they are the normal prefixes that we use in inorganic chemistry, right? Like 5 means pent, 6 is hex, 7 is hept, so on and so forth. The ending, which is over here on the right, these are our endings, is going to be dependent on if there's a single, double, or a triple bond. All right, so like, let's say we looked at 1, 2, 3, 4, 5 carbons, right? We have a chain. It's, Vesper tells us it's not going to be in a straight line, right? They're going to try to get away from each other. So this would be 1, 2, 3, 4, 5 carbons. So 5 is pent. So this would be pent. And they're all single bonds. So I would say ane, pentane. All right. If I did 4, 1, 2, 3, 4, this would be propane. All right. And now you know why methane is called methane, right? It's 1 carbon, all single bonds. And so this is methane. We can't draw a stick structure, a simplified structure for methane because it's just 1 carbon. It would look like that. And so we have to draw it out. Now, when we name simple hydrocarbons, there are pretty simple rules, all right? It says the first thing we have to do is identify the longest continuous chain. And this is important because up to this point, we haven't talked about side groups, all right? Life would be pretty dull if there were no side groups on organic molecules. So we have to identify the longest continuous chain, and then we'll figure out a way to name the side groups in a moment. We're going to number from the end closest to a side group. That way our side groups have the smallest possible numbers that they can have. The side groups are named alphabetically. So like F comes before meth, or bute comes before prop. And instead of an ending like ane, ene, or ine, we're going to change the side group ending to YL. So a methyl group is a single carbon sticking off the chain, right? Or a ethyl group is 2 carbons sticking off the chain. We'll see that in a minute. We then name the parent chain, and we use numbers to tell us where each of our side chains is. So that looks really complicated. Let's actually just do it in practice, and we'll see what we got. So this is heptane, right? It's got 7 carbons. It would look like this. Now let's say we have a side group right here, all right? This would be 1, 2, 3, 4, 5, 6, right? So At position number 2, we have a side group. Right, here is our side group. And we've numbered it left to right this time because we want the side group to have the smallest number possible. We wouldn't want to start over here so that the side group is 5. So we say 2-methyl, side group is methyl at position 2, and then we just say hexane because it's a 6-carbon chain and they're all single bonds. So that would be 2-methyl hexane, and this is what that would look like. All right. Now notice, it doesn't matter which side I put the side chain on, all right? I can number it from either end. So in this case, I would start on the right and go left, with carbon number 1 would be the furthest to the right. All right, now let's move it a little bit. We have another side chain here. So now we're at 1, 2, 3, 4, 5, 6. So this is going to be 3-methyl hexane, all right, just like that. Now, if you have multiple bonds, all right, we're just gonna add that into the name. We're gonna add in the ene or the ine or whatever, and we're still gonna follow the same set of rules. We want the longest continuous chain to have the multiple bond in it. We want to number from the end closest to the multiple bond, and we want to name the side groups in alphabetical order, just like before, and we want to name the parent chain. So let's look at that. So I've got 2,4,4 trimethyl 2-pentene. All right, this is the condensed structural formula up top. We can ignore those hydrogens. All right, and so this is what we're looking at. And so when we want to name this, all right, let me switch over to a different color real quick. There we go. All right, we have the 2,4,4 trimethyl 2-pentene. So I'm going to go 1, 2, 3, 4, 5. There's my longest chain. At position 2, I have the double bond. So at 2, I have the double bond. All right, that's really hard to see, isn't it? Let's go with red. All right, so let's try that again. 1, 2, 3, 4, 5. There we go. At position 2, we have the double bond. So that's the 2-ene, 2-pentene. All right. At position 2 and 4, we have methyls. We have a total of 3 methyl groups. So we say at 2, 4, and 4, there are 3 methyl groups. This is 1 carbon sticking off the chain. So that's a methyl group. All right. Let's look at this one at the bottom here. There's our condensed structural formula. Here's our name, 4,4-dimethyl-2-hexene. All right, let's name it. 1, got to start on the right this time. 2, 3, 4, 5, 6. So at position 2, I have a double bond. So 2-hexene is the ending. The parent chain is 6 carbons long, so that's where I get the hex from. And at position 4, I have 2 methyls. So 4,4-dimethyl. All right. So the name is supposed to be really, really, really descriptive. All right. That's the point. Let's see if we can name these. All right. So propine is a pretty interesting molecule. Hopefully we can just look at that one and we can see. All right. We've got a triple bond. So that explains the YNE. We've got prop, which tells us, right, meth, eth, prop. So there's 3 carbons. All right, and that's what we're looking at in propine. So it would be a carbon with a single bond to another carbon, and then our second carbon is triple bonded to our final carbon. Now, you might ask, well, where are the hydrogens here? Well, we would have a hydrogen on the right. We would have 3 hydrogens on the left of this structural drawing there. All right, so look something like that. Now, we've got a really complicated one here to look at the very end. And the thing about these really complicated molecules is the same rules apply to them that apply to all of our other molecules, right? So let's just start by numbering it out, right? So we're going to number it first. Because if we can get the numbers down, the rest becomes, just learning how to put your functional groups on there. So let's start here. So I want my functional groups to be the lowest possible numbers, and I want my bonds to be the lowest possible numbers. So since I have functional groups at position if I number it from the left, 2, and a multiple bond at 3. But if I go from the right, I don't have a functional group until I get to 1, 2, 3, 4, 5. I need to start at the left. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are my group. There's my numbering system. So I know that it's going to end in deca something. All right. Now, I also know, all right, just because, I'm looking at this molecule, I've got a bunch of methyl groups. So I have 3 of them. So I have 3 methyls, 3 methyl groups. All right. They're at position 2. So that's going to be 2, 2, and 6. All right. So there is methyl number 1, methyl number 2, and methyl number 3. I also have a propyl group, right? So prop is 3 carbons. So I have 1, 2, 3 right there at position 5. So I have a propyl group at position 5. All right, at position 4, okay, we have an ethyl group, meth, eth, right? 1, 2. So I have 1 ethyl group, and it's at position 4. Okay. And then I look for my bonds. I have a double bond at position 3 and position 5. I have a triple bond at position 7. So those are everything I have to put into, in my parent chain, my parent chain is 10 carbons. So let's look at the name. Here's the name. All right. We've got, let me get this eraser here. Let me get rid of that. There we go. So we have 4-ethyl, 2,2,6 trimethyl, 5-propyl, 7-ine, 3,5-decadiene. All right, let's break that down and look at the name overall and compare it to our drawing here. So remember the rule says we want to name functional groups in alphabetical order. So E, then M, then P. All right, just like that. All right, I put the numbers out front. So at position 4, which we already knew, we had an ethyl group. At 2 and 2 and 6, we have 3 methyl groups, so 2,2,6 trimethyl. At position 5, we have a propyl group. Now at the end, I've got 2 double bonds and I've got 1 triple bond. So I'm going to put my 1 triple bond in and label where it's at. So 7-YNE, so 7-ine. And then I'm going to use 3,5-ene to finish for my double bonds. Now, I'm not going to ask you to name anything nearly as complicated as this, but I want you to see that the rules that you use to name something like propine, or in this case, this would be 1 propine, right? Because we would number 1, 2, 3, and we have to say where the I and E is, so 1 propine. I'm not going to ask you to name anything as complicated as the second one, but the rules are the same. And if you are planning to go on in chemistry and take organic chemistry at college, this would be something that you would want to be able to do. But it starts with understanding the basic rules, right? So those are the basic rules. Now, when you look at this molecule, you might think, oh, this is a static molecule. It's just going to sit there. Well, that's not really the case. We have something called isomerism in organic chemistry. And a structural isomer, right, isomerism, isomer, occurs when molecules that have the same molecular formula arrange in different ways. So what might that look like? Well, here's C4H10, which is butane. We know it's got 4 carbons in a row. It has the exact same formula, C4H10, as 2-methylpropane does, right? So let's make sure that we see that. So 1, 2, 3, 4 carbons. All right, it's an alkane, so we're 2N plus 2. So C4H2 times 4 plus 2 is C4H10. All right, same thing here. We have carbon, 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 carbon. So we have 4 carbons, right? And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens for everybody to be the same. So this is the same formula. Well, that's not that one. There we go. But it's two different structures. So that's called isomerism. And isomers are important in organic chemistry because remember, there is a relationship between structure and function. So butane is going to act differently. It's going to have different characteristics than 2-methylpropane would have. So let's wrap up this introduction by looking at some of the important molecules. So for petrochemicals, things we should be familiar with when we hear that word: gas, kerosene, Vaseline, propane, plastics, anything that comes from oil. For biological molecules, think your macromolecules from your biology class, right? DNA, RNA, proteins, lipids, carbs, all your hormones, insulin, dopamine, all that stuff. If it's a molecule in the body, it's a biological molecule, right? For pharmaceuticals, think of vitamins. Those are going to be important. Think of aspirin, think of insulin. Those are the ones that you're most likely to see. And then for polymers, all right, any of the polys, all right, so polyethylene, that stuff like that, polyvinyl chloride, PVC, right, that we make our pipes from for our plumbing. Nylon is a polymer, Kevlar is a polymer. And then there's a little bit of overlap between your biological molecules because DNA, RNA, and all your proteins are also polymers. What is a polymer? Well, poly means many. Mer comes from the Greek word for unit or part. So polymer is many parts. So that implies that there are monomers or single parts that build them up. So hopefully you remember from biology that the monomer for a protein is an amino acid. These are the amino acids. And you can see that these are very clearly organic molecules, right? They're carbon-based molecules. They all have the same uh, root, the same base molecule, which is this carbon with a NH3 on one side and a carboxylic acid on the other, and then some R, some functional group, all right, and an H there. Okay, so they all have that same basic structure, but they are obviously organic molecules, so we talk about them. And these 20 amino acids, depending on the order that you put them in, make all of the different proteins in your body. There are polar amino acids, there are non-polar amino acids, there are acid or like acidic amino acids, basic amino acids, so they're kind of color coordinated here. A polypeptide, which is another name for a protein, is comprised of a bunch of amino acids chained together. And here you can see where that chain is occurring, like that repeating unit through the middle. So these are all your amino acids that are now bonded together to make this protein. Remember, there's a relationship between structure and function. So the shape of the protein and the job that it does are related. And the way that you get the shape that you want is by putting the right amino acids in the right order. Now, moving on to some of the petrochemicals I want you guys to be familiar with in this unit. Methane is really important. All right, it's a greenhouse gas. It's produced as a byproduct of agriculture. We use it for generating heat and light. It has a pretty large impact on the environment, right? And we'll talk some more about that in the unit, and you'll see some of that in the textbook. Make sure you're familiar with plastics, all right, especially how they break down. So there are some risks with using plastics. Most people think like, plastics, they don't decompose. Well, they don't decompose biologically, but they do break down into something called a nurdle or a mermaid tear. And these are like little teeny tiny microplastics that as the plastic breaks down into smaller and smaller pieces, they can become caught in the gills of fish, or they can mess with the krill populations. I mean, they can really be a major pollutant in the ocean. There is a pretty large patch of plastic out in the Pacific Ocean. It's called the Great Pacific Garbage Patch. It's about twice the size of Texas, and it's just a bunch of plastic floating around. It's pretty disgusting. Now, that's not to say plastics aren't important. Obviously we use plastics to store our food. They're great for transportation. They're really important for space travel, right? They can shield radiation. They don't weigh a whole bunch, but we need to be careful how we use them. And if we can develop bioplastics, which are, plastics that can be broken down biologically, that's, a good thing for the environment. Make sure you know that plastics are formed from ethylene. All right, that is the base molecule, the base organic molecule that we use to make plastics, and it comes from petrochemicals. So, like when we separate out gas and diesel and all that stuff from oil, one of the byproducts is ethylene, and we use it to make plastic. We're going to talk a little bit more about pharmaceuticals. All right, pharmaceuticals are the drugs that we use in our day-to-day life. Something I want you to understand in chemistry, as far as our focus on pharmaceuticals, is the molecular shape of the drug determines what the drug does. All right, so if you want to go into medicine, all right, eventually you're gonna have to understand how a drug interacts with the cells inside of a person. So remember, structure and function is related. Now, there are a lot of different drugs that come from chemists. Something that I've always thought was interesting is that 50% of the top 10 prescriptions written in the US all started as plant derivatives from the Amazon. Um, we get a lot of our drugs from natural sources, right? We take a molecule that we find in nature and then we manipulate it to do something that we want it to do. So there are a lot of really interesting drugs there. And we'll look at some pharmaceuticals later on in the unit. Now, we can also, when we talk about pharmaceuticals, look at vitamins. Okay. And vitamins are molecules that our body can't make, they have to come to us through the food that we eat. So in the US, we're fortunate enough to have what's called diet fortification, where the government ensures you get your vitamins. So, like, they put iodine in the salt to make sure, like, you get iodized salt, which is good for your thyroid gland. We get school lunch, which everybody, school lunch is gross, but it does have a certain amount of vitamins. It has to meet, like, check off some boxes to make sure that kids get their vitamins. Now, that's not always the case. 100 years ago, people were sailing around on the ocean for long periods of time. They would get scurvy because they didn't get enough vitamin C. So, it's important that we get our vitamins. That's obviously a good thing. But that's going to fall under discussion of pharmaceuticals and organic chemistry. All right. So hopefully this is a good introduction for organic chemistry for you. You might want to go back and rewatch the part on naming once or twice just to make sure you get a handle on it. Remember, I'm not going to ask you any of those massive molecules, but we do need to know how to name the basics. If you have questions, reach out, let me know, send me an email.